Hello my curious friend, and a very warm welcome to the Deepfield channel. Tonight we will journey together down to the pulsating heart of our galaxy, that mysterious place located exactly at the centre of the Milky Way, hidden behind veils of cosmic dust like a secret the universe has kept for billions of years. I promise to try and make this journey so smooth and hypnotic that sleep might arrive before we even reach our final destination. But before we embark on this dive into the heart of the galaxy, I would love to know in the comments which corner of the world you are listening to me from tonight. It is always a joy to discover that these words cross oceans and time zones to reach you. And if laziness is already setting in, just leave a simple hello. It might seem like little, but this small gesture shows the platform that our space is welcoming and helps us bring more tired minds to relax with us. If you enjoy our scientific journeys, please also leave a like and subscribe, and to those of you who are already part of our community, my heartfelt thanks. If you want to get even closer, consider becoming a channel member. Members get early access to videos before anyone else. The link is in the description. Now, wherever you are, find a very comfortable position. Sink into your pillows, relax your shoulders, let go of the weight of the day. If sleep comes, accept the invitation. Let us begin. There are nights when you look at the sky and see a whitish band crossing the darkness from horizon to horizon, like a veil of light poured by invisible hands. Most people pass by this sight without stopping. Perhaps you have done this. Perhaps you pointed it out to someone beside you and said something like, "It is the Milky Way," before going back to what you were doing. It is almost ironic. We are looking at our own galaxy, at the structure that contains us, that contains the sun, the earth, the moon, everything that has ever existed in human history, and we treat this spectacle as mere background. But there is a question we rarely ask while contemplating this band of light. A question simple in form yet dizzying in depth. What is exactly at the centre of it all? Where does this entire structure point? What lies in the heart of the Milky Way? To start answering, we first need to understand where we are within this structure, because our position inside the galaxy is in itself one of the most disorienting things astronomy reveals to us. When you look at that band of light in the sky, you're not looking at the galactic centre head-on. You are looking from the inside out from a position roughly 26,000 light-years away from the galactic core. Imagine an immense city, a stellar metropolis with hundreds of billions of inhabitants, and you live in a quiet neighbourhood, quite far from downtown, on a calm street in a spiral arm called the Orion Arm. The city centre is there, pulsing with energy and chaos, but you live in the outskirts, where things are relatively quiet. This distance of 26,000 light-years needs to be absorbed carefully, because our brains were not built to handle scales like this. A light-year is the distance that light, travelling at roughly 300,000 kilometres per second, covers in an entire year. That alone is a number that escapes any human intuition. Now multiply that distance by 26,000. The result is the space separating our solar system from the heart of the Milky Way. The light leaving the galactic centre at this exact moment will take 26,000 years to reach our eyes. By the time that light finally reaches us, all of recorded human history will have passed more than twice. And yet, somehow, we feel the influence of this centre. The gravity of the galactic core participates in the immense orbital ballet that makes the Sun revolve around the centre of the galaxy once every 225 million years, approximately. We call this period a galactic year or cosmic year. The Earth is just over 20 galactic years old. The dinosaurs existed less than 1 galactic year ago. All of human history, from the first stone tools to modern space telescopes, occurred in a tiny fraction of a single galactic day. Now, the first great myth that needs to be gently undone is that of the Milky Way as a flat, uniform disk, like a porcelain plate sprinkled with stars. This simplified image misleads more than it clarifies. The galaxy is a three-dimensional structure of extraordinary complexity, with spiral arms twisting outward from a central core, wrapped in a diffuse halo of ancient stars and dark matter that extends far beyond the visible disk. The disk itself has a varying thickness, being thinner in the outer regions and thicker and denser as it approaches the centre. The Milky Way belongs to a category of galaxies called barred spirals, and that word barred is fundamental to understanding the architecture of our cosmic home. At the centre of the galaxy, there is not just an isolated point of activity. There is an elongated structure, almost like a bar or a baton of densely packed stars, crossing the core from side to side. From this central bar, the spiral arms we see curling outward emerge. Think of a water whirlpool. In the centre there is a region of high concentration and turbulence, and from it, filaments expand in graceful curves. The central bar of the Milky Way works analogously, channeling gas and stars into specific movement patterns that fuel the entire galactic dynamics. The central core of the Milky Way, the region we call the galactic bulge, is a flattened sphere of extremely dense ancient stars. While in the spiral arms, like our Orion arms, stars are relatively spaced apart, in the bulge this density increases dramatically. If the solar system were located inside the bulge, the nights would be perpetual glares, with so many nearby stars that the sky would never know complete darkness. The stars in the bulge are mostly old, formed in the earliest epochs of the galaxy's existence, when the universe was still young and primordial gas condensed with a ferocity that is not repeated in the same way today. But there is something even deeper inside the bulge, something that took decades to confirm, sparked heated debates among astronomers, and only revealed itself thanks to instruments capable of seeing beyond visible light. The interstellar dust permeating the galaxy acts as an opaque curtain for human eyes and common optical telescopes. When we point a regular telescope at the galactic centre, we see only darkness, or at most a diffuse, indistinct glow. The true heart of the Milky Way remained hidden for centuries of astronomy, concealed behind dust clouds with the same efficiency as a veil hiding a face. It was only with the development of radio astronomy in the first half of the 20th century that astronomers began to realise something extraordinary was happening at the galactic centre. Radio waves pierce through interstellar dust with an ease that visible light never could, and the first radio telescopes began picking up intense, strange emissions coming from the direction of the constellation Sagittarius, exactly where the galactic centre should be. They identified a compact, powerful radio source, eventually named Sagittarius A, and within that region discovered an even more concentrated and energetic source, dubbed Sagittarius A star. For decades, astronomers debated the nature of Sagittarius A star. The compactness of the source, the intensity of the radio emission, the peculiar behaviour of stars orbiting the central region, all pointed to something of colossal mass concentrated in a minuscule space. Hypotheses piled up, but definitive confirmation required more precise observations than available technology allowed. What was there? What was the nature of this invisible object bending the orbits of stars around it as if they were leaves in the wind? The answer that would emerge from the following decades of observation and analysis would be one of the most unsettling and fascinating confirmations in the entire history of astronomy. Not because it was completely unexpected, at least not for theorists, but because it transformed something that existed in the realm of mathematical equations into a concrete, demonstrable reality, observable through real data and patient decades of stellar tracking. To understand what was being confirmed, one must first grasp a concept Einstein elaborated in the early 20th century that still challenges intuition today. Gravity, in the Einsteinian description, is not a force acting at a distance like an invisible hand. It is a curvature of space and time itself, caused by the presence of mass and energy. The greater the mass concentrated at a given point, the greater the curvature around that point. In extreme cases, this curvature can become so pronounced that nothing, not even light, can escape the region immediately surrounding that point. This region is what we call a black hole. The idea of an object from which not even light can escape is one of those notions the brain receives and immediately tries to reject. because it goes against all sensory experience accumulated over a lifetime. We are used to a world where things have surfaces, edges, where we can, at least in principle, move away from any object if we apply enough force. A black hole violates this intuition absolutely. There is a boundary around a black hole called the event horizon, and beyond this limit the curvature of space-time is so extreme that all possible trajectories of any particle, of any photon of light, point inward. There is no trajectory leading outward. The event horizon is not a physical surface you would touch. It is a point of no return defined by the geometry of space-time itself. What made the case of the Milky Way's centre particularly intriguing was the scale of the object observation suggested. We were not talking about a stellar mass black hole, those that arise when massive stars reach the end of their lives and collapse on themselves. We were talking about something of a completely different category, a class of objects whose masses exceed our Sun's mass by millions or even billions of times. A category astronomers call supermassive black holes, which seem to exist at the centre of practically every large galaxy we know. The question beginning to form in researchers' minds as evidence accumulated was one that still echoes today in the deepest conversations of astrophysics. Where does the energy animating this system come from? What feeds the heart of the galaxy? What sustains the frenetic activity hinted at in the data, visible in radio emissions, X-rays, and observations of stars dancing around the centre at speeds defying any simple explanation? There is an image that helps understand everything about to be revealed. Imagine holding a stone over a bottomless well. Your fingers open, the stone falls. As it falls, it gains speed, and this speed is a form of energy that did not exist when the stone was resting in your hand. Gravity did not create energy from nothing. It converted one form of energy into another. The stone had potential energy from being elevated relative to the bottom of the well, and this potential energy transformed into kinetic energy in the accelerated motion of the fall. The deeper the well, the more intense the gravity at the bottom, the greater the speed the stone reaches, the greater the energy released at the moment of impact. Now imagine the well has no bottom, that the gravity at the centre of this well is of an intensity no stone, no imaginable stone could resist. That space itself around this centre curves so profoundly that even light, the fastest thing in the universe, cannot escape after crossing a certain limit. You're imagining the neighbourhood of a supermassive black hole, and the energy feeding the heart of the Milky Way comes exactly from this principle, from the most extreme gravitational fall nature can produce. The word physicists use to describe this process is accretion. It comes from Latin, meaning growth by addition, gradual accumulation. But in the context of a supermassive black hole, accretion is not a calm process. It is violent, turbulent, and extraordinarily efficient at transforming matter into energy. When gas, dust, fragments of destroyed stars or any form of matter gets too close to a supermassive black hole, it does not fall straight in. It begins to orbit, just as water swirls around a bathtub drain before being sucked down. This orbit is not circular and stable. It is an inward spiralling path. Spiralling matter loses angular momentum bit by bit, and as it loses angular momentum it falls into inner orbits, closer to the black hole where gravity is more intense. All this falling, rotating matter forms a structure astronomers call an accretion disk. Imagine a flat spinning disk like Saturn's rings, but infinitely denser, hotter, more agitated. The inner layers of this disk spin faster than the outer layers, and this speed difference generates friction. Friction generates heat, heat of an intensity defying common language. The interior of an active accretion disk can reach temperatures far exceeding the surface temperature of our Sun. At these temperatures, matter does not exist as solid, liquid, or common gas. It exists as plasma, a state of matter where electrons are stripped from atoms and everything is a cloud of electrically charged particles. And hot plasma radiates. It emits light at wavelengths ranging from radio to the most energetic X-rays. That is why when astronomers point their telescopes at the centre of galaxies with active supermassive black holes, they see a luminosity that can outshine the entire host galaxy combined. Here is what makes this process so extraordinary from a physical standpoint. The efficiency with which an accretion disk converts matter into energy is far superior to any other process we know. When the Sun burns hydrogen in its core through nuclear fusion, it converts about 0.7% of the fuel's mass into energy. It is a remarkable process, sustaining all life on Earth. But an accretion disk around a black hole can convert between 10 and 40% of the matter's mass into pure energy, depending on the black hole's spin speed. 10 to 40%, compared to 0.7% for nuclear fusion. Gravitational accretion is, in terms of energy efficiency, the most powerful process nature knows. The physical law governing all this has a name sounding too simple for the weight it carries. It is called conservation of energy. In its most basic form, it states energy cannot be created or destroyed, only transformed from one form to another. When matter falls toward the supermassive black hole at the Milky Way's center, it is not creating energy. It is converting gravitational potential energy into heat, light, radiation, motion. Conservation of energy is the principle explaining why the galactic center shines, why it emits radio, why it emits X-rays, why stars around the black hole move so fast. Everything is conversion. Everything is transformation of one energy form into another. But there is a second law complicating this picture profoundly and revealingly. It is called conservation of angular momentum. To feel what it means before naming it, think of a figure skater on ice. Spinning with arms out, they spin slowly. Pulling arms close to the body, they spin rapidly. They are not generating new energy. They are preserving something, a quantity physicists call angular momentum, the product of mass, velocity, and distance from the rotation axis. When distance decreases, speed must increase to keep the product constant. Now apply this principle to matter falling toward the supermassive black hole. This matter starts very far away, slowly rotating around the galactic center. As it approaches, it must spin faster to conserve its angular momentum. That is why the accretion disk exists. Matter cannot fall straight in because angular momentum forces it to orbit. And it is this angular momentum transforming a silent direct fall into a turbulent spiral, into a high-temperature disk, into an energy source radiating across the entire galaxy. Without angular momentum conservation, there would be no disk. Without the disk, no extraordinary heat. Without the heat, no radiation. What seemed merely an abstract physics law is actually the invisible architect of the entire energetic structure of the galactic center. There is a third law coming into play when matter is so close to the black hole that general relativity effects begin to dominate. Albert Einstein described it early last century, and for decades it seemed more a work of mathematical art than a description of something physically real. General relativity tells us gravity is not a force acting at a distance, as Newton imagined. Gravity is the curvature of space-time itself caused by mass and energy. A massive object curves space around itself, and other objects move along these curvatures. What we call free fall is actually the straightest possible motion in curved space. Around a supermassive black hole, this curvature becomes extreme. Space-time is not slightly bent, like around the sun. It is twisted, coiled, so profoundly curved that the laws of space and time we use daily cease to be valid. Time runs slower near the black hole than far from it. Orbits that would be stable in any other gravitational context become unstable and precarious. Matter in the innermost accretion disk is subject to effects only general relativity can describe accurately. Without Einstein, without the work he developed over a decade of intense reflection, between the early and late 1910s, we simply would not have the mathematical tools to understand what happens in that region. The human history behind these discoveries is a story of patience and instruments needing invention before questions could even be asked. Early last century, the Milky Way was poorly understood. Its size was not certain, its center's location unknown, and the idea of something extraordinary there was pure speculation. American astronomer Harlow Shapley, working in the early 1920s, was among the first to realize the Sun was not at the galaxy's center, and that the galactic center lay roughly towards Sagittarius, many thousands of light years away. But seeing the center was impossible with common optical telescopes. The Milky Way's center is hidden by immense thicknesses of interstellar gas and dust absorbing and blocking visible light almost totally. We had to wait for radio astronomy to develop after World War II for humanity's eyes to finally begin piercing that veil. In 1956, Australian astronomer Frank Kerr and colleague Jan Hendrik Oort mapped neutral hydrogen structure in the galaxy using radio wavelengths, and for the first time, a clearer view of the central region was possible. But it was in the following decades that hints of something truly extraordinary began accumulating with growing force. Radio observations revealed an intense point-like emission source right at the galaxy's geometric center. It was named Sagittarius A star, a technical notation hiding a monumental discovery. As radio telescopes improved, as X-ray telescopes were launched into space to observe the sky above Earth's atmosphere, the image grew sharper and more unsettling. Something small, compact, and immensely energetic lay in the Milky Way's heart. The definitive turning point came with the work of two astronomer groups who, for decades, pointed infrared telescopes at the galactic center and tracked individual stars' movements over years. One group led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Germany, and another by Andrea Ghez at the University of California, Los Angeles. Both tracked the trajectories of stars orbiting the galactic center, and what they saw eliminated any reasonable doubt. The closest stars describe orbits only explainable by a colossal mass concentrated in an extremely small volume. One star in particular, called S2, completes an elliptical orbit around the center in about 16 years, reaching speeds approaching 3% of light speed at its closest point. Using Kepler's third law, relating orbital period to the mass it orbits, they calculated the focal point's mass equals about 4 million solar masses. 4 million suns compressed into something smaller than our solar system. Genzel and Ghez shared the Nobel Prize in Physics in 2020 for these discoveries. The fundamental imbalance making the galactic center work is an imbalance between forces. On one side, gravity pulling everything inward to the center, wanting to compress, condense, gather. On the other, radiation pressure and heat generated by the accretion process itself, pushing outward, dispersing gas and dust, potentially halting new star formation nearby. This tug-of-war between gravity and radiation is not static equilibrium. It is a dynamic dance changing over billions of years, where sometimes gravity dominates and more matter falls, intensifying accretion, and sometimes radiation dominates and expels material, reducing available fuel. The galactic center breathes, in a way. It has periods of higher activity and relative quiet. Today, the supermassive black hole at the Milky Way center, Sagittarius A star, is in a relatively calm period. It is not devouring large amounts of matter. Most surrounding gas was either expelled or consumed in earlier epochs. But even in relative quiet, it is not invisible to modern instruments. In March 2022, the Event Horizon Telescope collaboration revealed the first direct image of Sagittarius A star, a luminous ring of hot plasma around a central shadow, the shadow of the event horizon, the boundary beyond which nothing returns. It was the most direct visual confirmation of everything decades of indirect work had suggested. Now, inside this accretion disk, on a much smaller scale than we're used to thinking, something happens that is just an instance of a repeating principle. A gas cloud falls, it heats up, it radiates, it loses some angular momentum to the neighbouring cloud, and that neighbouring cloud falls a bit further inward, where the process restarts with more intensity. It is a cycle, a cascading mechanism where each local event feeds the next. Each approaching matter fragment releases energy interacting with surrounding matter, heating, compressing, accelerating the next fall. A single gas filament falling towards Sagittarius A star traverses this transformation path locally, releasing energy in a small region, disturbing surrounding plasma, sending pressure and radiation waves outward. And when you stop thinking of it as an isolated filament, when you start imagining what happens when this process repeats simultaneously at countless points around the black hole over thousands and millions of years, something completely different begins taking shape on a scale we have not finished describing. When you observe the process from the outside, when you try to see not a single falling filament, but the entire ensemble at once, something unexpected happens in your perception. What seemed chaotic begins revealing lines. What seemed random begins obeying contours. Not because someone drew these contours, not because some central force decided to organize the mess, but because physics repeats its behaviors scale after scale. And when behaviors repeat on a sufficient scale, patterns emerge by necessity, like bubbles rising in water without anyone summoning them. The first thing this large-scale organization reveals is a structure astronomers call the central molecular zone. It is not a discrete object, not an edge you could touch, but a region with properties so distinct from the rest of the galaxy it functions as its own domain, with its own rules, average temperature, characteristic density. This zone occupies a region a few hundred light-years in radius around Sagittarius A star, and within it, gas does not behave like the gas in the outer galactic disk where we live. Out here, gas is cold, sparse, organized in relatively simple clouds following nearly circular orbits around the center. In there, gas is hot, agitated, disturbed, organized in structures moving in extremely eccentric orbits, plunging very close to the center, then rising back to comfortable altitudes, like comets around the sun but on a galactic scale. This behavioral difference is not accidental. It is the fingerprint of Sagittarius A star and everything immediately surrounding it on the environment. The energy emanating from the central region, whether as radiation, particle winds, or shock waves from ancient explosions, imprints a memory on the surrounding gas. The gas remembers, so to speak, being heated, pushed, accelerated. And this memory translates into movement patterns persisting long after the original energy source weakened or changed. Inside the central molecular zone lies an even more fascinating substructure. There is a ring, or something approaching a ring, of dense hot molecular clouds orbiting the center a few dozen light-years away. Astronomers identified this decades ago via radio and infrared observations, immediately intrigued by its geometry. It is not a perfect ring, not continuous. More like a broken necklace, where some pearls are present, others lost or not yet arrived, and the thread connecting them is more a tendency than a rigid structure. But the tendency is clear enough to have a name, to be studied for decades, to reveal precious info on how matter is transported toward the center. What this irregular ring of clouds does is serve as a sort of waiting room. Matter arriving from the outer galaxy, surviving initial disturbances and heating, stays here in orbit, slowly losing stability. Collisions between ring fragments, mutual gravitational interactions, continuous heating from internal radiation sources all conspire to push some ring matter even closer to the center. The ring feeds what is further in, just as the galactic disk fed the ring, just as spiral arms fed the disk, in a cascading transport system spanning tens of thousands of light-years. Inside the molecular ring lies an even more compact energetic region. There is a cluster of ionized gas clouds astronomers call Sagittarius A, and within it an even smaller structure called the mini-spiral. The mini-spiral is, exactly as the name suggests, a system of hot gas filaments curving around Sagittarius A star in a pattern resembling a miniature galaxy's arms, compressed to a scale of just a few light-years. It was mapped in extraordinary detail in recent decades via radio and near-infrared observations, and every time new instruments increased resolution, new complexity layers within it were revealed. What the minispiral represents is precisely the emergent organization no component planned. No individual gas filament decided to curve the right way to create a spiral arm. No particle consulted neighbours before following its trajectory. What happened is the combination of gravity, rotation, radiation pressure, and mutual collisions over thousands of years selected surviving trajectories, and surviving trajectories in an environment with rotation and gravity gradient tend to have spiral geometry. The spiral was not planned, it was distilled. This is the essence of emergent organisation in physics, a principle astronomers took decades to fully appreciate in the galactic centre context. For a long time, people looked at the central environment's complexity trying to find a single mechanism explaining everything, a primary cause generating all visible structure. But nature rarely works that way in complex systems. What exists is not a single cause but a web of mutually reinforcing causes, and the structure emerging from this web is more than the sum of individual parts. American astronomer Jan Oort was among the first to insist the Milky Way's centre needed systematic attention as an independent study object. In the late 20th century, long before technology allowed seeing the centre directly in dust-piercing wavelengths, Oort argued from radio data the central region contained a mass and energy concentration inexplicable by the same rules governing the galactic disk. His work did not solve the mystery but put the problem on the map unignorably. Others came later building on this foundation. Following decades brought better instruments and cascading revelations. When new generation infrared telescopes began piercing the dust cloud obscuring the centre in visible light, what astronomers saw was disturbing in the best way. Stars. Stars in abundance. Young stars, massive stars. Stars that should not exist so close to a supermassive black hole, according to the era's theoretical understanding. The presence of these young stars, just a fraction of a light year from Sagittarius A star, became known as the paradox of youth, revealing that matter organization in the galactic center generated consequences existing models did not predict. The explanation emerging over following decades involved exactly the large-scale organization processes we are describing. The young stars at the center would not have formed where they are today. Either they formed further out in a gas disk existing a few million years ago, dense and organized enough to spawn stars despite intense gravitational tides, or they arrived from afar already formed, brought by energy exchange mechanisms with other stars. Whatever the explanation, it requires prior matter organization in a coherent structure, a disk or organized flow, making possible what diffuse field models made impossible. This perception profoundly changed how astronomers think about the galactic center, not as a place where physics behaves radically differently, but where normal physics operates in extreme conditions producing extreme results, seeming like anomalies until you understand the conditions. The paradox of youth is not a principle violation. It is a consequence of conditions no terrestrial lab can reproduce, but theory, with careful adjustments, can describe. System geometry plays a crucial role in how organization emerges. The Milky Way is not a sphere. It is a flattened disk, and this flattening means matter falling toward the center arrives preferentially in a plane, the galactic plane. This alone creates symmetry organizing processes. But there is more. The Milky Way has a central bar, an ellipsoidal structure of stars and dark matter, extending a few thousand light years on each side of the core. This bar does not rotate at the same speed as surrounding disk material, and this speed difference creates resonances, disk points where matter is systematically pushed inward or outward, where stable orbits become unstable, where material accumulates before finally being released to fall deeper. The galactic bar functions as an angular momentum transport mechanism on a galactic scale, exactly analogous to what happens locally in accretion disks but operating over incomparably larger distances and times. It twists gas trajectories, forces encounters otherwise would not occur, creates conditions for material flows finding the path of least resistance toward the center. Numerical simulations of the galactic center, including the bar, produce structures much closer to telescope observations than simulations ignoring it, confirming it is not a detail, but an essential system component. On even larger scales, the spiral arm's shape itself interferes with matter flow to the center. Spiral arms are increased density regions moving through the disk at different speeds than individual stars, like a wave moving through a crowd without always being composed of the same people. When gas enters a spiral arm region, it is compressed, relative speed changes, and some gas fractions end up on trajectories taking it progressively further inward. The galactic center is not isolated from the rest of the galaxy. It is connected by causal chains spanning tens of thousands of light years in time periods, covering much of cosmic history. What emerges from all this multi-scale organization is something astronomers sometimes call the ecology of the galactic center. The term is borrowed from biology for good reason. Just as a forest ecosystem is more than the sum of individual trees, and species relations create dynamics no single species could produce, the galactic center is more than the sum of its components. The interaction between Sagittarius A star, surrounding gas disk, young and old stars, molecular clouds, magnetic field filaments and heated plasma creates a collective dynamic with emergent properties. One emergent property is self-regulation. The system has mechanisms tending to moderate its own excesses, at least in certain phases. When Sagittarius A star accretes too much matter at once, released energy heats surrounding gas, increasing pressure and making it harder for new matter to fall. This reduces accretion rate, reducing released energy, allowing gas to cool again, eventually allowing new matter to start falling, restarting the cycle. This feedback regulation is common in complex systems from biology to climatology, and its presence in the galactic center suggests the system has a sort of dynamic equilibrium, not static but continuously adjusting to receive perturbations. But this dynamic equilibrium is not unconditional, it can be broken. It was broken in the past, and signs of these breaks are still visible in the surrounding environment, written in structures extending tens of thousands of light years above and below the galactic plane. The large-scale organization described so far, with all its elegance and emergence, is actually just the current state of a system that was once much more violent, carrying scars of episodes where something beyond ordinary accretion, something of completely different scale and intensity, swept everything around and redesigned the entire environment. And understanding what happened in these episodes, what can amplify the ordinary process enough to change the galaxy, requires an ingredient not yet named, transforming the continuous whisper of accretion into a cry crossing cosmic history. The amplifier is gas, not gas in any poetic or metaphorical sense, but real, dense, cold molecular gas, invisible to common light, flowing toward the galactic center on paths taking millions of years to traverse. This gas is the raw material for everything. It feeds the young, violent stars surrounding Sagittarius A star. When accumulated in sufficient quantities, it plunges into the black hole's gravitational well, triggering something not describable as mere accretion. It can only be described as an eruption. Gas's apparent simplicity hides a complexity taking decades to understand. Gas does not fall in a straight line. It does not obey a simple trajectory like a stone thrown in a well. It is turbulent, magnetized, alternately heated and cooled by competing forces on very different time and space scales. And when this gas gets close enough to the central black hole, crossing certain dynamic boundaries and starting to spiral inward, continuously tightening, it begins releasing energy in a way no ordinary nuclear process could imitate. Mass-to-energy conversion efficiency in supermassive black hole accretion can reach 10 to 40% of total accreted mass. For comparison, solar nuclear fusion converts less than 1%. This means the Milky Way's central black hole is, energetically, tens to hundreds of times more powerful per mass unit than any existing star. But efficiency alone does not explain past violence. For this efficiency to translate into a galactic-scale eruption, gas must arrive in much greater quantities than today. Here the amplification mechanism enters in all its elegance and brutality. When density waves sweep the galactic plane, when two galaxies approach and gravitational tides deform spiral arms, or when the galaxy's own differential rotation creates instabilities, gas is compressed, channeled, pushed inward. It converges on the centre not because directly attracted, but because lateral paths were closed by perturbations. Like all river tributaries, dammed simultaneously, leaving only the path to the valley bottom. When this massive gas influx reaches the galaxy's inner regions, the central molecular zone, where gas density is already hundreds of times higher than the outer disk, it finds an environment already operating at the limit. Massive stars form there at rates consuming any other environment in millions of years. Stellar winds and supernova explosions continuously inject energy into surrounding gas, and the magnetic field there is so intense, hundreds of times stronger than the disk's average, organizing gas into filaments seemingly defying gravity, vertical and ordered, as if something below was pulling the field into specific geometry. When extra gas arrives, all this cascades. The cascade starts with increased accretion rate onto Sagittarius A star. More falling gas means more released energy. More released energy means more radiation pushing surrounding gas outward. More outward push means gas above and below the galactic plane begins being swept away, with a force having no everyday equivalent. Imagine a steam jet from a boiler, but instead of steam, it is superheated plasma. Particles accelerated to significant light speed fractions, magnetic fields twisted by falling material rotation, and radiation across all electromagnetic spectrum frequencies. And this jet lasts millions of years, tens of millions of years. This process has a name astronomers use with near-professional affection: active galactic nucleus feedback. The term active galactic nucleus, often abbreviated AGN, designates any galactic nucleus where the central black hole is accreting material at rates producing luminosities far exceeding the combined luminosity of all host galaxy stars. Variations of this denomination carry their own histories, observations from different eras with different instruments, before underlying unity was perceived. Quasars were first discovered as point-like radio sources when radio telescopes systematically swept the sky, called quasi-stellar objects, because they looked like stars in optical photos but emitted far more radio energy than any star should. When distances were determined via spectral shifts, it became clear they were among the most distant, thus oldest observable objects, with absurd luminosity for any known source. Decades passed before consensus emerged. Quasars are active galactic nuclei seen in an extremely intense accretion phase, usually in young galaxies or those having just merged, receiving huge fresh gas injections. Seyfert galaxies were catalogued by Carl Seyfert in the early last century as spiral galaxies with unusually bright nuclei and high ionization emission lines in spectra. They represent a less extreme version of the same phenomenon: active galactic nuclei with more modest luminosities, more frequently found in the nearby universe, where mergers are less common and pristine gas reservoirs largely consumed. Nomenclature was created without knowing Seyfert was describing a smaller version of the same engine-fueling quasars. Blazars are an even more particular case. When the plasma jet emitted by the active galactic nucleus points directly at the observer, relativistic aberration amplifies apparent luminosity by factors up to dozens of times the real value. A blazar is not fundamentally different from a quasar or Seyfert galaxy. It is just the viewing angle making the jet appear extraordinarily bright. Discovering astronomers could not know this, and the name remained as a reminder of an era when these objects seemed to belong to a completely different category. And there are also radio galaxies, where the dominant element is not the nucleus's optical luminosity, but radio emission produced by immense plasma lobes extending beyond the visible galaxy body. These lobes, sometimes larger than the entire host galaxy, are fossils of plasma jets launched by the active nucleus over tens of millions of years. They expand through intergalactic medium, displacing hot gas-filling galaxy halos, eventually dissipating into diffuse structures radio observations detect long after the jet itself ceased. The Milky Way is none of these things today. Sagittarius A star is quiescent, accreting so little its current luminosity is, by an extraordinary margin, the lowest among all supermassive black holes we can compare in similar galaxies. But the Milky Way was, in the past, an active galactic nucleus of some sort. Not on a quasar scale, almost certainly, but enough to leave persisting marks. And these marks are structures known as the Fermi bubbles. The Fermi bubbles are two immense gamma-ray emission lobes extending above and below the galactic plane, each about 25,000 light-years across, totaling 50,000 light-years high. Discovered in Fermi Space Telescope data, launched early this century dedicated to gamma-ray astronomy, the discovery impact was comparable to any recent astronomical discovery. No one expected this. Simulations of gamma-ray emission distribution along the galactic plane did not predict such large, well-defined symmetric structures, and when data was carefully processed removing known contributions, bubbles emerged with nearly circular edges, as if blown by something acting at the exact galactic centre. Discussion on Fermi bubbles' origin is not closed. Two main candidates exist, current data not definitively ruling either out. First is an intense star formation episode at the galactic centre a few million years ago, where a massive star creation burst collectively produced enough winds and supernovae to inflate bubbles with necessary energy. Second is an activity episode of Sagittarius A star itself, a transient high accretion phase where the central black hole briefly functioned as a low-luminosity, active galactic nucleus, emitting enough jets or winds to create bubbles. Both mechanisms need careful quantification, and total bubble energy, estimated over 100,000 equivalent supernova, must be explained by any successful theory. There is a way to bring this abstraction closer to direct experience. Looking at the sky on a clear night, far from artificial lights, seeing the Milky Way's pale band crossing horizon to horizon, you see the galactic disk projection on the celestial sphere. The brightest, densest region, towards Sagittarius in the southern hemisphere, is the galactic center direction. You cannot see Fermi bubbles with your eyes, as they emit predominantly in gamma rays, high-energy light completely invisible to biological detectors in your head. But they are there, right now, slowly expanding outward from the galactic plane, persisting as fossilized memory of something happening millions of years ago, not yet fully understood. There are also radio structures known as non-thermal filaments, discovered toward the galactic center aligning perpendicularly to the galactic plane with non-accidental regularity. These filaments are magnetic field wires made visible by relativistic electrons, accelerated near light speed, emitting synchrotron radiation spiraling around field lines. They exist for tens to hundreds of light years, just a few light years thick, origin still debated. But their mere existence indicates the galactic center environment is electrically and magnetically organized in a way having no parallel in the outer galactic disk where the sun is. All this, Fermi bubbles, magnetic filaments, hot turbulent molecular gas of the central molecular zone, circumnuclear rings spinning at speeds destructive to any solid object, forms a system which, observed in a cosmic snapshot, seems in equilibrium. Energies balance, flows compensate, central gas average temperature, star formation rate, Sagittarius A star luminosity, all today in a low-intensity regime compared to the past. But this equilibrium is not stable like a stone at a bowl's bottom. It is stable like a stone on a hilltop, as long as no force pushes it either way. And then something changes, not abruptly, not with a warning sign any surrounding civilization could detect early enough to understand what is about to happen. Change begins internally, in the very mechanisms sustaining that precarious equilibrium described. The hilltop stone begins to oscillate because the hill itself is not perfectly symmetric, because cosmic wind blows from directions varying over millions of years, because matter continues falling toward the center in ways neither uniform nor predictable. What pushes Sagittarius A star out of current lethargy could be anything in a frighteningly varied catalogue of perturbations. A gas cloud with enough mass crossing the black hole's influence radius and spiraling inward on a trajectory unable to escape by mere orbital inertia. A star cluster, slowed by gravitational tides and collisions with dense central molecular zone gas, losing cohesion and depositing dozens of stars in orbits, taking them dangerously close to the event horizon over millions of years. Or something even more dramatic, merging with a smaller galactic nucleus, bringing its own supermassive black hole spiraling inward while disturbing surrounding gas and star structures. Each trigger acts differently, but all converge on the same initial effect: increased accretion rate. More matter reaching the accretion disk per time unit means more energy released per time unit. Disk heats up. Emitted radiation increases in luminosity. Expelled particle winds become more intense. And here physics begins revealing its most counterintuitive aspects, because an accretion system does not behave like a gradually opened faucet. It behaves like a system with multiple operating regimes separated by potentially abrupt transitions. In the low accretion regime, where Sagittarius A star is today, matter flow is so scarce gas cannot even cool efficiently before crossing the event horizon. It falls into Sagittarius A star in a sort of hot diluted flow, releasing energy relatively inefficiently. Astronomers call this regime radiatively inefficient accretion flow, a name capturing exactly what happens. Energy is there, gravity doing its job, but conversion to observable radiation is surprisingly low. That is why Sagittarius A star with 4 million solar masses shines with luminosity corresponding to a tiny fraction of similar systems in other galaxies. It is underfed in the most literal technical sense. When accretion rate increases beyond a critical threshold, the system can jump to a different regime. Gas cools enough to form a geometrically thin, optically thick accretion disk, the iconic object in black hole visualizations photographed in Galaxy M87's nucleus. In this regime, gravitational energy to radiation conversion efficiency rises dramatically. The same black hole, same gravitational mechanism, can shine dozens or hundreds of times brighter, simply because matter is arriving in sufficient quantity to sustain this thin disk. Sagittarius A star's luminosity could, in principle, jump from current value to something comparable to a moderate active galactic nucleus, without Sagittarius A star itself changing at all except how much it is eating. The threshold concept here is fundamental. There is no smooth, linear transition between a supermassive black hole's sleep and awakening. There are bifurcation points where the system can choose between radically different states depending on deterministic conditions, but practically impossible to predict with necessary precision from observations made 26,000 light-years away. Physicists studying these systems sometimes use chaos theory language, not because the system is chaotic in the popular sense, but because small initial condition differences in a falling gas cloud can produce dramatically different accretion trajectories. The event perhaps most sharpening astronomers' imagination in recent decades was tracking an object called G2, initially detected as a gas cloud approaching Sagittarius A star on an irresistibly fatal trajectory. G2 provoked heated debate and huge expectations. If a massive enough cloud crossed the black hole's tidal radius, it would be destroyed and scattered in a gas tail, eventually feeding the accretion disk. Models predicted possible Sagittarius A star flaring. Telescopes worldwide pointed at the galactic center, and then G2 passed near the black hole, slightly disturbed in structure, but survived, indicating it was likely denser than a simple gas cloud, perhaps two merged stars enveloped in gas. Sagittarius A star did not awaken, but the episode left an important legacy, demonstrating the galactic center environment can produce objects defying simple classifications, and the relationship between what falls toward the black hole and what it actually ingests is mediated by rich, complex physics not fully understood. But when awakening truly happens, when accretion rate crosses the critical threshold sustainedly, following phenomena are built in mutually amplifying layers. The heated accretion disk emits ultraviolet and X-ray radiation in quantities ionizing surrounding gas in a rapidly growing volume. ionized gas regions, visible as characteristic emission lines in astronomical spectra, expand outward from the nucleus like waves. Simultaneously, radiation pressure and particle wind from the heated disk begin blowing disk gas outward along black hole poles, creating relativistic jets. These jets are not collimated light beams like cosmic lasers, though tempting to imagine. They are plasma flows, charged particles accelerated to significant light speed fractions, confined and directed by magnetic fields, coiled in helical geometry around the black hole rotation axis. Jet structure reflects magnetic field structure, which reflects accretion disk geometry, which reflects falling gas trajectory. Everything connected in a causal chain, extending from event horizon to hundreds of thousands of light years. Observing and measuring these phenomena from Earth requires coordinated effort remarkable in itself. The galactic center is hidden behind interstellar dust layers so thick visible light cannot significantly pierce them. The main observation window is near-infrared, mid-infrared, radio waves and X-rays. Different telescopes, at different wavelengths, capture different aspects of the same object. Chandra X-ray. Observatory records X-ray flares. Sagittarius A star regularly exhibits. Luminosity increases lasting minutes to hours, representing tens or hundreds of times resting brightness. These flares happen a few times a day, exact mechanism still debated. Could be magnetic reconnection in the accretion disk, or ingestion of small gas clumps or asteroid or comet fragments getting too close, or disk instabilities producing localized extreme heating regions. The Event Horizon Telescope, that global collaboration combining radio telescopes across continents to effectively create an Earth-sized telescope, managed to resolve Sagittarius A star's shadow in radio waves, confirming the compact object at the galaxy's center has a size compatible with a 4 million solar mass black hole. But observing Sagittarius A star at this wavelength is notoriously difficult, because the galactic center itself is full of gas scintillating and distorting radio waves just as Earth's atmosphere scintillates visible stars. Each observation is an exercise in patience and technical sophistication, combining atmospheric corrections, instrument calibrations, and image reconstruction algorithms in a mathematical dance lasting months after each observation campaign. Models astronomers use to predict Sagittarius A star's intense mode behavior are computer simulations running on supercomputers for weeks. They solve general relativistic magnetohydrodynamics equations, meaning they track magnetized plasma behavior in regions where special relativity effects, near-light speeds, and general relativity, extreme space-time curvature, are equally important. No simplification is possible in this regime. Physics is fully relativistic, fully magnetic, fully turbulent, and the only way forward is brute computational power guided by mathematical formulations taking decades to develop. Even so, simulations cannot simultaneously cover all relevant length scales, from event horizon at Schwarzschild radius scale for Sagittarius A star, about 12 million kilometers, to Fermi bubble scale, extending tens of thousands of light years. No existing or near-future conceivable computer can simultaneously solve scales differing by over 18 orders of magnitude. What models can say with good confidence is that an active mode Sagittarius A star is not simply a brighter current Sagittarius A star. It is qualitatively different. Magnetic field structure changes, accretion flow geometry changes, jet shape and power change. An impact on surrounding environment changes in ways propagating outward over millions of years, progressively affecting regions further from the galactic center. While you rest, somewhere in the observable universe, a supermassive black hole is right now crossing one of these thresholds, jumping regimes, firing a pair of jets beginning to reshape its host galaxy over next millions of years, and photons carrying news of this event are travelling in all directions while Earth sleeps. Structures forming when Sagittarius A star is in intense mode have persistence. They do not disappear immediately when accretion rate drops. Jets, once fired, continue propagating by their own inertia, an internal pressure long after the source calmed. Heated and expelled gas takes tens of millions of years to cool and potentially return. Fermi bubbles, whatever their formation mechanism, represent energy deposited in the galactic halo continuing to exist as high-energy particles and amplified magnetic fields. The universe has memory. Each activity episode leaves traces persisting far beyond the episode itself. History layers written in plasma, radiation, and magnetic fields. Astronomers of the distant future will read like we read tree growth rings or ice core layers today. And these phenomena, as we begin realizing when looking at everything the galactic center produces, do not happen in complete isolation from the rest of the galaxy or the wider universe around. The galaxy does not exist as a closed island. This perception, though seemingly obvious when stated, took decades to be genuinely incorporated into how astronomers build galactic center models. For a long time, intellectual habit was treating the Milky Way as self-sufficient, processing internal resources according to internal logic. What recent decades' observations revealed, with insistence becoming impossible to ignore, is the galactic center is in constant dialogue with environments extending far beyond conventional visible galaxy borders. The main partner in this dialogue is the circumgalactic medium, a vast reservoir of hot, diffuse gas enveloping the entire galaxy in a sphere hundreds of thousands of light-years in radius. This reservoir is not empty or passive. It contains enough mass to profoundly alter future galaxy behavior, exchanging matter and energy with the galactic disk and center in ways we are just beginning to map accurately. When Sagittarius A star goes through higher activity and expels high-energy winds, these particles do not just vanish in empty space, they travel outward, eventually slowing upon encountering denser circumgalactic medium gas, transferring momentum, thermal energy, and high-energy particles to it. The circumgalactic medium absorbs this deposit and stores it for an extraordinarily long time. But flow does not only go inside out. The circumgalactic medium, by its own gravitational dynamics and neighbouring galaxy influence, can be perturbed in ways sending gas back toward the galactic centre. This infalling gas is called circumgalactic medium accretion, representing a fuel source feeding star formation in the galactic disk and, in more dramatic episodes, potentially increasing material flow eventually falling towards Sagittarius A star. There is thus a large-scale cycle. Galactic center expels matter and energy. These exit to halo and circumgalactic medium, and eventually some returns, possibly triggering new activity. Time to complete this whole cycle is on the order of 1 to several billion years, a scale making the cycle invisible to human civilization, but evident when comparing galaxies at different evolutionary stages. The most direct, best documented feedback cycle, however, happens on much shorter timescales and between much closer components. The central molecular ring star formation zone, a few hundred light-years from the black hole, provides gas-feeding young massive stars present there. These stars, living brief, intense lives, radiate extraordinary ultraviolet energy, ionizing surrounding gas and heating the environment. Heated gas expands, creating pressure that, in some regions, inhibits new star formation by preventing smaller clouds from gravitationally collapsing. But in other regions, this same pressure can compress adjacent clouds, precipitating collapse, creating a new star generation. The young star cluster known as IRS-13 and other dense clusters near the center are the visible result of this feedback process, where previous star generations paved the way for following ones by altering surrounding medium physical conditions. There is also feedback directly involving the central black hole. When material falls into Sagittarius A star, part of the gravitational energy is converted to radiation, and particle winds exiting the black hole's immediate environment and heating nearby gas. This heating reduces the rate gas can cool and fall further inward, creating a self-regulation mechanism. If the black hole started accreting too fast, it would generate more energy, heat more gas, reduce its own feeding rate, This negative feedback is responsible for Sagittarius A star's apparent current calm, at least compared to other galaxies' active nuclei. This regulatory mechanism's efficiency determines whether a central black hole grows explosively or moderately over its host galaxy's life. In the short term, meaning decades or a few centuries, the galactic center seems a relatively stable, predictable place within the extraordinary patterns established throughout this journey. Sagittarius A star will remain essentially inactive on the luminosity scale we know. Central cluster stars will continue orbits calculated with increasing precision. X-ray and infrared flares will occur with frequency similar to recent decades. Astronomers making infrared observations 50 years from now will see a recognizable galactic center, though with instruments whose capabilities would be hard to imagine today. This short-term stability is not trivial. It is the product of that delicate force balance described, and its maintenance depends on no large magnitude external perturbing factor coming into play. On the scale of a few thousand years, genuine uncertainties begin emerging. The gas cloud known as Cloud 1, a structure tens of times our Sun's mass observed, approaching the black hole on trajectories leading some astronomers to predict a spectacular collision a few years ago, revealed more complex physics than expected. The cloud survived periapsis, the closest approach point, leading to model revisions on how gaseous objects behave in extreme conditions near Sagittarius A star. This episode was itself a lesson on prediction limits. Even with highly precise positions and velocities, objects' internal physics can produce unexpected behaviors. In a few thousand years, other clouds will follow similar trajectories. Some will produce observable flares, some will be destroyed. The line between predictable and unpredictable in these events depends on initial conditions we can never measure with absolute perfection. On the million-year scale, the panorama transforms profoundly. The central molecular ring is not static. It is fed by gas migrating inward to central galaxy regions over time, and this migration is accelerated or slowed by gravitational interaction with the galactic bar, the elliptical star structure crossing the Milky Way's center. In tens of millions of years, the central molecular ring may have accumulated enough gas to trigger a much more intense star formation episode than current, comparable to distant starburst galaxies. This episode would in turn feed stellar winds and supernovae, which together could create favorable conditions for substantial Sagittarius A star activity increase. We would then face a galaxy which, viewed from hundreds of millions of light-years away, would suddenly seem brighter in its nucleus. Sensitivity to initial conditions is here an obstacle not merely technical, like insufficient instruments or computing power, but fundamental. The galactic center is a nonlinear system where small present condition differences produce radically divergent future trajectories. The exact gas mass crossing Sagittarius A star's gravitational influence radius over the next million years depends on subtle gravitational perturbations accumulating chaotically. The speed gas in certain clouds cools depends on specific molecule abundance catalyzing radiation emission, and these abundances depend on the cloud's irradiation history, which depends on which massive stars existed nearby in past epochs. The dependency chain branches indefinitely, and at each branch is an uncertainty that, however small, amplifies over time. Recognizing these limits is not intellectual failure. It is, conversely, one of the scientific method's most mature demonstrations, the ability to precisely delimit territory where reliable statements are possible and where they yield to informed speculation. Astronomers studying the galactic center are, among scientists, perhaps most accustomed to working on the frontiers of the knowable, because their study object is simultaneously the most extreme and inaccessible in the Milky Way. Each new telescope generation pushes this frontier a bit further, not eliminating mystery but revealing a new question layer the previous generation did not even know to formulate. And it is precisely on this frontier science finds something approaching what is normally described as wonder, not the superficial wonder of mere enormity, easily becoming cliché in astronomy, but a deeper, quieter wonder emerging from understanding how extraordinarily distinct things connect unexpectedly. The fact that the closest black hole, an object classical physics would call a singularity point where equations lose meaning, is also the generator of jets and winds regulating how many stars are born across the galaxy. And these stars in turn regulate the environment, determining the black hole's activity rate, is a causal chain transcending any intuition developed in our daily lives in mild-scale worlds. This system's beauty resides partially in its capacity to surprise even after decades of intensive study. Every time a model seemed mature enough to be considered definitive, observations brought data requiring revision. The light echo illuminating distant gas clouds reveals activity episodes occurring before any modern telescope existed, needing incorporation into the recent Sagittarius A star history portrait. Fermi bubbles, invisible light and non-existent in pre-high energy astronomy models, represent one of the largest structures identified in the Milky Way, and must be explained by any theory describing galactic center behavior over the last millions of years, and the orbitometric precision tracking individual stars around the black hole, capturing in measurable trajectories the influence of an object no eye will ever see directly, is itself a triumph, combining decades of observation patience with theories born in abstract contemplation sophistication. When looking at everything explored, the black hole and immediate environment, stars orbiting in patterns impossible to explain otherwise, particle jets and winds extending hundreds of light years, echoes, bubbles, and magnetic fields weaving all this complexity into a coherent structure, we begin realizing there is an underlying order not immediately obvious but progressively revealing as pieces fit. Not a simple order, not a machine whose functioning is explained on one page, but an order of the same kind found elsewhere when looking closely enough at systems seemingly chaotic at first glance. This perception, slowly emerging as data accumulates and models mature, is perhaps what distinguishes galactic center study from mere cataloguing of extraordinary phenomena. What astronomers are finding beneath the seemingly irreducible complexity of all these processes interacting across multiple time and space scales is a surprisingly small set of principles which, in different combinations and parameter domains, generate all this behavioral richness. Gravity, collapsing clouds, curving orbits, trapping light, radiation pressure, resisting, expelling, heating, magnetic field storing energy, guiding particles connecting distant regions, and thermodynamics determining where systems evolve when released to follow their own path. 4 languages which, in different combinations, write the history of the most extreme place we can call home, this turbulent heart residing 26,000 light-years towards Sagittarius, invisible to the naked eye, present in everything we are. These 4 languages mentioned do not exist in parallel, like separate book chapters readable in any order. They exist in constant dialogue, each responding to others, each being modified by others, each generating conditions feeding back the whole system in ways physicists call nonlinear. Technical word for something intuition immediately recognizes as fire or storm nature. Systems not behaving proportionally to received impulses, systems gently pushed for a long time without apparent response and then suddenly completely reorganizing into a new configuration. The galactic center is, above all, a feedback system, and to understand what this means in deserved depth, we must contemplate how these feedbacks operate in 2 fundamentally opposite senses. Some amplify, driving the system further from equilibrium until something must give, and others stabilize, bringing the system back when it strays too far, creating what thermodynamics recognizes as a steady state, not quiet, not motionless, but sustained in a dance of tensions mutually cancelling on average, even if never cancelling at any particular instant. Amplifying feedback begins when a dense enough molecular cloud starts gravitational collapse. As it collapses, it heats. As it heats, internal pressure increases, but if massive enough, gravity overcomes this growing pressure and collapse continues. Core heats further, density increases further, center gravity becomes even more intense. Each process step creates conditions for the next to occur faster, more intensely, so what began as a slow interstellar cloud contraction ends in catastrophic collapse. This is amplification, and in the galactic center it operates on scales making any terrestrial storm seem a whisper. But the universe does not collapse entirely, and the reason is stabilizing feedbacks exist. When Sagittarius A star goes through intense activity, consuming material and expelling radiation and particle jets, this very process heats and disperses surrounding gas, reducing the rate new material falls toward the black hole. Black hole eats less. Activity decreases. Surrounding gas gradually cools and begins moving inward again. Cycle restarts. This oscillation between activity and quiet is not accidental. It is structural. It is how the system regulates itself, just as a thermostat regulates room temperature, except the thermostat was engineered, and this was spontaneously generated by physics laws operating on gas and gravity for billions of years. What emerges from these cross-feedbacks is something physicists call self-organized criticality, a state where the system perpetually maintains itself on the edge between order and chaos, collapse and dispersion, frantic activity and complete silence. At criticality, small perturbations can trigger events of any size, from a tiny hours-long flare to a galactic-scale eruption, taking tens of millions of years to fully dissipate. It is a delicate yet extraordinarily robust state, because the system does not need external adjustment to stay in this regime. It naturally drifts toward criticality from very diverse initial conditions, but there is an even deeper dimension rarely receiving deserved attention when speaking of the galactic center, and that dimension is chemistry. Interstellar space is not empty. It is permeated by surprisingly complex molecules, built by the same stellar nuclear synthesis processes, creating every element heavier than helium in the universe, distributed through space by supernova explosions and dying star winds, then reorganized into increasingly elaborate structures in cold, dense clouds, where ultraviolet radiation protection is sufficient for chemical bonds to survive. In the galactic center, this molecular chemistry reaches density and diversity unparalleled anywhere else we know nearby. Sagittarius B2 and Sagittarius B1 clouds, belonging to the central molecular ring, contain organic molecule concentrations astronomers detect via radio signatures, each molecule vibrating and rotating at characteristic frequencies, traveling to our radio telescopes like coded messages. Ethyl alcohol in quantities making any terrestrial distillery seem irrelevant. Ethylene glycol, antifreeze-based substance. Glycolaldehyde, a simple sugar detected in star-forming regions as a potential RNA sugar precursor. Precursor amino acids. Nitrogen and sulfur molecules in combinations continuing to surprise astrochemists whenever new radio observatory data arrives. This chemical richness is not irrelevant to the larger galactic center narrative. It is integral to it. The same massive stars enriching the interstellar medium with heavy elements during life and death are creating conditions for this molecular chemistry to thrive. Dense clouds where chemistry is most complex are the same where the next star generation is forming. Planets forming around these stars will inherit this chemical legacy, starting their histories with a much richer molecular repertoire than existed in early universe first planetary system generations. There is progression here, elaboration advancing generation by generation, each stellar birth and death cycle leaving the environment a bit more chemically complex than found. And then we reach the level where systemic vision becomes not just useful but necessary, the level realizing the galactic center cannot be understood piece by piece, its essence residing precisely in connections between pieces. The central black hole cannot be understood without the central molecular ring feeding it. The central molecular ring cannot be understood without the magnetic field structuring its filaments and regulating its star formation rate. The magnetic field cannot be understood without massive stars whose winds and explosions continuously inject energy into it. Massive stars cannot be understood without molecular chemistry providing building blocks they emerge from, and molecular chemistry cannot be understood without nucleosynthesis history starting in first stars and unfolding over billions of years of stellar cycles. It is an integrated system in the deepest sense, not integrated like a machine whose parts fit because designed to, but integrated like an ecosystem, where each component exists in relation to others, where removing any element would irreversibly change all others' nature, where the whole is genuinely more than the sum of parts, because part interactions generate behaviours no single part could produce. Emergence is the word scientists use for this phenomenon, and it is one of the most beautiful and unsettling in all science philosophy. A black hole is a simple, inevitable consequence of general relativity equations applied to high enough density. A turbulent magnetic field is a consequence of electromagnetism equations applied to moving plasma. A glycoldehyde molecule is a consequence of quantum chemistry laws applied to carbon, hydrogen, oxygen atoms at low temperatures. Each element in isolation follows rules writable on half a math page. But put these elements together, let them interact for billions of years, and what emerges is something no individual equation anticipates, something having genuine novelty quality, something only existing as a result of all the accumulated interaction history. The galactic centre is emergence on a cosmic scale. The four languages identified, gravity, radiation pressure, magnetic field, thermodynamics, are simple in fundamental expressions, but in combination, in iteration, in dialogue over timescales exceeding our imagining capacity, they write a complexity history astronomers are still learning to read, and deep down, when peeling back all complexity layers, following all threads back to origins, what we find is something sayable very simply. The galactic centre is essentially the consequence of the universe, trying to distribute energy as efficiently as possible. All its dramaturgy, every particle jet, an exploding star and a reorganizing magnetic filament and organic molecule synthesized in cold interstellar space, is an expression of this universal tendency, moving energy from where concentrated to where it has not reached. Sagittarius A star is not monstrous or violent because it decided to be. It is simply an extraordinarily efficient redistribution mechanism, the largest our galaxy produces, transforming falling gas gravitational potential energy into radiation, heat, motion, spreading across the galaxy. Every supernova ever exploding in the central molecular ring was redistributing energy. Every organic molecule forming in a dense cloud was storing energy in chemical bonds, awaiting the moment it would be released again. Every S-star orbit around the central black hole is a system dance finding a configuration where energy can be kept in balance for now, while the system awaits the next perturbation forcing it to find a new balance. This reconnects every element explored to a single central idea. The crazy orbit stars defying our star formation understanding are gravitational energy reorganizing into new configurations. X-ray flares pulsing from the galaxy's heart are sudden accumulated energy redistributions. Fermi bubbles rising tens of thousands of light-years above and below the galactic plane are echoes of energy redistributions occurring in some remote galactic past. Magnetic filaments crossing the central region like invisible tapestry threads are channels where energy flows from one form to another, particle motion to field, field to radiation, radiation to heat, heat back to motion. And molecular chemistry, this most unexpected and perhaps most personally relevant dimension discussed, is energy patiently stored in atomic bonds, waiting, as always in the universe, for the transformation moment. There is something profoundly reassuring about this when we can sit with this idea long enough to let it be fully absorbed. The most extreme place in our galaxy, where forces are most intense, processes most violent, conditions most inhospitable to any quiet or peace notion, this place follows the same rules governing every energy transformation ever occurring anywhere in the universe. Same rules governing heat emanating from a cooling teacup on a table. Same rules governing how the body releases food energy during sleep. Same rules operating in same fundamental directions, producing on unimaginable scales what they produce on intimate scales. The universe is consistent with itself across all scales and domains. This consistency is perhaps the most wonderful thing science discovered, that the same simple laws writable on paperwork equally in the first instance after everything began, and in the galactic center depths, and in chemical reactions keeping every cell alive while you read these words. You're 26,000 light-years from the Milky Way's center. You're safe. Between you and the galaxy's turbulent heart lies a vast expanse of space and time, stars and dust clouds, gentle magnetic fields and spiral arms spinning in a cadence disturbing nothing around you during a human life's entire eternity. The central black hole continues existing, as it always has, in a quiet, only occasionally disturbed. Gas filaments continue dancing along magnetic fields, in a dance not ending and not needing to end. Fast orbit stars continue spinning around that invisible point, describing their perfect ellipses in space. Everything is in its place. The universe cares for itself with a patience exceeding all our capacity to measure patience. And in this care, in this imperturbable consistency of laws governing everything from atoms composing your bones to galaxies forming billions of light years away, there is something we can call, without exaggeration, reliability. The universe is reliable. It follows its laws. It distributes energy according to patterns we can know, and which, once known, reveal not chaos but an order of disconcerting depth. You are part of this order. Atoms composing every cell in your body were forged inside stars, and some of those stars lived and died in the galaxy's center, in this very place we spent so many moments contemplating together. You carry the galactic center within you, literally, in the elements making your existence possible. You have always been part of this. While you rest, the Milky Way's center continues doing what it always did, redistributing energy, forming stars, feeding the black hole with the patience of geological eras multiplied by thousands, maintaining the dance kept since before any eye existed to observe it. You do not need to do anything now. There is nothing to solve, nothing to understand more completely tonight, no problem that cannot wait until dawn. Let thoughts become slower, like molecular clouds expanding in vacuum, each softly dissolving into surrounding space without resistance, without urgency. The universe cares for you. You're safe in this moment, in this place, in this breathing, resting body built by billions of years of cosmic and biological evolution, precisely for this purpose, to exist, to perceive, to rest. Everything is in order. The galaxy spins. The center pulses softly in its radio and X-ray silence, 26,000 light-years away, unreachable and simultaneously part of the same history you inhabit. Magnetic fields extend, stars continue their paths, and you, made of the same matter that made all this, can rest now. The universe continues its silent dance, and we rest in its embrace. Thank you for walking with me tonight. Sleep well.